let's go ahead and get started now that old man story time is over. My original plan was to kind of finish up Lecture 3 and sort of jump into the next topic today, especially given that a lot of you aren't here for the career fair, and also kind of switching doesn't work that well for these two topics. I think what we'll do, and we'll take the appropriate amount of time, I think we'll just finish up this topic and then call it good for today. We've been working our way kind of slowly through it. Where we left off last week is we were talking about this high-level topic of scanning and enumeration. We haven't really done much scanning or actual enumeration yet. What we've primarily focused on is just host discovery. Is the host up? Is something listening? Is there a machine at that particular IP address? Whereas typically we're interested more in terms of, yes, is there a host at that IP address, but then also what is listening, what services, what is happening at that particular host. So when we talk about scanning, that's the process of attempting to connect to the machine in a more meaningful way, trying to figure out what services or applications are running on that target device. And enumeration just means kind of just listing out the knowledge we can gain about a device or set of devices. So while last week we used Nmap just to check if various hosts were up, primary purpose, or the original purpose of Nmap, is really just to be a port scanner, to scan and figure out which ports are potentially listening to traffic and available to connect. As we've seen, we will continue to see it does other things and does other things well, but traditionally, historically, that is what Nmap was meant to use. I list here some of the classification of the state a port can be in. One thing I should mention is that these are not really official sort of networking terms. These are really just Nmap's perspective as to what state a port can be in. It's still useful, at least I would say those first three useful states here. Other tools may just have things as sort of opened or closed, but the mechanisms that Nmap uses allow it to determine whether, first off, it's open, whether it's accepting connections, closed. We can tell that there's something there, but it's no services are listening on that port, or it has some mechanisms to determine to what extent a port is filtered. Can't quite determine whether the port is open because as we're attempting to reach this port, we're getting things that are not being returned back, that are being dropped along the way. And I ask here, why would it be filtered? But I think we know there's some sort of firewall or other monitoring service that is sitting in between or alongside the host we are attempting to connect to and the computer we are running Nmap from, and it's actively doing some work to prevent that kind of port scanning from happening here. I promised to explain the mediocre memes I added to these slides, but now that you've made some decent progress right on Lab 2, and many of you are done with it, maybe you have a feel for what's happening, why it's kind of, okay, not funny, why it's explainable. So he starts with the default Nmap command, gets a response back, host seems down. If it is really up, but blocking our ping probes, try -pn. Remember, that's kind of the two-state process here. First, we want to check if the host is actually up, and then we attempt the port scanning. Instead, if you pass -pn, you're saying, skip host discovery. I know that host is up, even if it's telling me because it's blocking the ICMP traffic like we talked about last week. Even though it's telling me it's not up, I know that it's up. So I know better. I know that the host is up. Oh, the response back is actually no hosts are up. Nothing is available at that IP address. And at that point, it's literally trying everything. So Nmap-A, really just try all approaches, highly verbose, provide a reason a connection isn't available, run every single script in the default script directory, and try all ports from 1 through 64K for that IP address. So the joke is we try something reasonable, we try something more careful, and then we just throw the chair. We try and throw the entirety of all of our tools at the host to discover if it was up. That command would take a very long time to run. Conceptually, and we did a little tiny bit of this last week, one can do port scanning via just connecting to a port. It was quick. We did that netcat command on a port 80 of that HTTP Everywhere site. That is, in a sense, a port scan. We attempted to connect at the application layer to port 80, and we got some traffic back. We did successfully scan that port. We have confidence that there is some service listening on port 80. That is valid. Also valid is actually just using our TCP/IP three-way handshake, newly corrected three-way handshake in the slides to just try to connect to that port. That is valid. The downside of that, as we'll kind of talk about, is sort of a trade-off between speed, stealthiness, and accuracy that we're making here. There are many other ways that Nmap can connect to a port, and I think as someone gaining more knowledge in this field of pen testing, of ethical hacking, it's an appropriate knowledge base to gain to have a high-level understanding. Some of this is Nmap specific, but some of it isn't, of different ways one can determine whether a port is up or down versus just trying to blindly kind of connect to the port. I bring open the kind of Nmap reference guide. You'll see some links have been clicked there. I certainly reference it. It's referenced in the lab manual as well. It is all there, every single option and a reasonable description of every single option. If you had read and fully digested the entire reference guide, you wouldn't need the remainder of today at least. It can be trying to tricky. You sometimes have to know what you're looking for first to find it in the guide. But my recommendation is, you're faced with an Nmap command or trying to understand how to do something, you should try to search through and look through this guide versus just attempting Google searches first. It's all fully documented in here. It's a very good and thorough and well-written guide built up over a couple generations here. It can get a little bit monotonous. Your mileage may vary. Maybe some of you are at the edge of your seat just waiting to hear about these next Nmap command line arguments. I'll keep inserting somewhat low effort means to keep it light. And there's the first one there. High level review, and I mentioned week one that this would still be pretty important when it came to this topic. Our TCP headers and the various flags that are available here that are part of how we establish that connection. So there's the data, there's whatever IP traffic we're passing alongside our TCP header, but specifically there are those flags that indicate different aspects, the purpose of the particular segment that's being sent. That is our request to connect, our synchronize, our acknowledge, our finish, our reset, and two others that are not as relevant are push and our urgent flags here. Think of it just as a single bit that is turned on or off or set or not set when we're sending our TCP packet here, and that is part of the way we connect to machines in general. Sometimes we just take it for granted that this is all kind of magically happening under the surface, and we say, well, there's TCP IP, things work. Now let's kind of dig a little bit deeper into it with, like I said, newly connected things. So the so-called full connection scan, that is kind of not the naive, but sort of the, if I asked you to figure out if a port was on, up, or down on a particular machine, you would probably do something like this. The full connection scan just attempts to complete the three-way handshake. Send a packet with the SYN flag, wait to hear back for something with SYN-ACK. So when I say that's both of those flags would be high for that return packet, send a follow-up packet with the ACK flag high. Every normal TCP connection is doing that three-way handshake. It is not the default in Nmap, so if you wanted to do it, it's -ST. And I mentioned last week, sometimes you can squint and understand why certain options have certain abbreviated versions. Have a cheat sheet, write some notes. I think that's your best bet for understanding what is what. Capital T could stand for full TCP connection, but maybe it does, maybe it doesn't. There's some value in this full connection scan. You don't need to be able to create really a custom packet to be able to do this. You don't have to have super user permissions on the machine you're on to be able to send a full connection scan, because it is kind of the default per spec way of creating a TCP connection to another device. It's going to be relatively slow. You may not think of this as being relatively slow because, well, it's just a few packets. What's the big deal? If you go back to here, and if we really want to know all the different possible services and ports that are open across all the different IP ranges, you are potentially talking about minutes, hours. I haven't heard of days, but a very long time to be able to do your full port scan. In that sense, sending this packet, determining what comes back, and completing that connection is relatively slow. It's also, when we talk about not being stealthy, and stealth is a relative property here, ultimately it's not really possible to be fully stealthy when doing a port scan. I am attempting to send traffic to a machine. There's bits on a wire. If there is some sort of intrusion detection or other stateful firewall running on that host machine, it is not just in theory, but it is in practice very possible for them to log that attempt. It can log every single packet sent. There's nothing that, as the pen tester, that I could do to prevent that from being the case. So stealth is always kind of a relative thing. In this case, we think of the full connection scan as being not stealthy, because it would be logged by basically anything that logs any kind of real network traffic. You would see it in your Wireshark. You would see it in any kind of intrusion detection system that, yes, this other host connected to this machine on your network, and it completed the connection. Depends on what your goals are, to the extent that not being stealthy is a significant downside or a minor downside. And again, keep in mind that it's not a binary thing. I've either been stealthy or I've not been stealthy. Ultimately, one cannot do a port scan without leaving a trace of some network traffic. There's a physical impossibility there. The question is, how much of a footprint did we leave? How much imprint did we leave that could potentially be either logged somewhere, or I guess efficiently analyzed to determine that, yes, there was an attempt to do this kind of scanning on the network. You can think of this as being the default to scan, but that's not quite correct. It's not Nmap's default, but it's kind of the default way to think about how one would determine if a port is up or listening or not listening. There's the half connection scan. It is the default that Nmap uses. It's arguably more stealthy, but in reality, what we're just doing is we're completing only part of the three-way handshake, 2/3 of the three-way handshake. So it's called half connection. It's kind of 2/3 of the connection. I guess if the connection requires two sides, one side thinks the connection is completed and the other side is not completing the connection. So that is one way to think of it, as a half connection scan. Because from a logical perspective, it kind of makes some sense, right? I am the person doing the port scanning. I'm just going back to the prior slide here. Once I get this, I'm good, right? I don't actually want to connect to the port. I don't actually, at least not yet, want to actually send data and have some sort of back and forth communication with a service hosted on that port. I just need to know that something's listening. I send the SYN. If I get a SYN-ACK, I haven't completed the handshake, but I know the other side's listening. The other side now is a little bit confused, potentially, as to what would happen. And it's such sort of a common thing that the stealthiness, the relative stealthiness, is sort of hand wavy in that any IDS that's looking for port scanning and maybe considering countermeasures is going to log that just as easily as the full connection scan. Looking at those other flags in our TCP packet leads us to three other types of port scanning techniques. The Nmap documentation refers to this as a subtle loophole in the actual spec for TCP that allows Nmap, the tool, to differentiate between open and closed ports. Now, what is also interesting, at least what I find interesting about this, is that you have this a number of things that are just extremely well spec'd out in terms of the TCP RFC. There's a link there. I won't open it up. Hundreds of pages at the end of the day when you include all the supplemental and related material about what it means to have a TCP connection and what not just the data fields, but other behavior as well. And despite all that, despite this true standardization of that, different systems interpret those standards differently. There's just code written by different humans and different teams of humans, and they interpret certain aspects of that to mean potentially slightly different things. Obviously, networking works as a general sense, but at least in terms of the edge cases, the non-traditional usage of the RFC is where you kind of get slightly different behavior here. So we have those flags in the TCP header, and there is no flag called null, so we'll talk about this. There's three different combinations of those flags that Nmap you can tell it to use to make three different types of connection attempts to that host at a particular port to determine, based on its best guess and based on certain interpretations of the TCP RFC, whether or not that port is actually closed or not. And this is a direct quote from the Nmap documentation here, that if the destination port is closed, if there's an incoming segment that doesn't contain a reset that causes a reset to be sent, it should cause a reset to be sent in response, then there's other documentation in the RFC as to what should happen when you start off by sending a packet that doesn't have SYN or reset or ACK set. If the port is closed, it's supposed to return a reset. If the port is open, maybe it's an edge case, maybe it's not fully specified, but default reading of the RFC says there should be no response back at all if the port is open. I'm listening on port 22. If I, for some reason, just get a FIN packet from a connection that hasn't even been initiated yet, I'm supposed to return nothing at all. I'm just supposed to completely just drop that and do nothing at all. Whereas, if the port was closed, if it's port 222, and I get a request to connect with just a FIN packet, I'm supposed to return a reset back. So that kind of tells you by the absence of a response whether or not that port potentially is open or not. With the edge case that you really shouldn't be sending, I guess that's one way to read the spec, these packets that are just FIN, push, or urgent along the way. This leads to 3 different types of scans beyond just sort of the half connection scan, which is you can send a TCP packet with no flag set whatsoever. Kind of a weird empty packet. Oh, here's just a packet. If the port's open, it's not supposed to respond. It's supposed to respond with a reset if the port is closed. What you will get back, though, from Nmap when you attempt these is, and I listed it on the slide, and I'm going backwards quickly here, as being closed or filtered is the response you would get back here. I'm getting nothing back. Excuse me, the open or filter. I'm getting nothing back. All that tells me is I got nothing back. So I have some evidence that potentially the port is open, but it could also be getting filtered as well. You're getting no traffic back, at least via sending one of these 3 types of TCP packets. You have some additional knowledge potentially, but not conclusive knowledge as to whether or not a port is open. So -SN is the null scan, null meaning none, no flags are being set. FIN is when you set specifically just the FIN flag and you set that one. And when you set the FIN, push, and urgent flags, that's referred to as the Xmas scan -SX here. Any idea why it's called the Xmas scan anyway? More lame programmer humor. You're lighting up lots of the flags. You're turning on a lot. If there was LEDs associated with it or in some sort of firewall or packet tracker, you're lighting up a whole bunch of the flags. You're lighting it up like a Christmas tree, and that's why they just call it the Xmas scan. How one would remember the flag or the command line argument is -SX. Otherwise, that's why we have a cheat sheet with us. That's why we take notes. So if you want to remember that, potentially for Thursday, it's called the Christmas scan, the Xmas scan, because it's just lighting up all the lights on the tree when it's sending that packet. Why try that? Why even have these options? For the same reason that we don't just do a full connection, right? We have some sort of potentially a firewall on the other side of our connection, and these are just different ways of attempting that connection. Maybe the default one doesn't work, maybe the half scan doesn't work. Well, let's try all these different types of scans and see what kind of responses we get back out. I do think personally, there's a little bit of a chicken and egg, issue associated with this, right? Not to get too kind of philosophical with you, but if you have a service running on a port, it has to respond to something, right? Again, we talked about kind of the fundamental limit there that if I have an SSH server, someone has to be able to connect to it. But if there's filtering associated with that, where perhaps it's based on IP level filtering or other firewall rules, none of these attacks are going to necessarily make that much of a difference, or none of these scans, are going to necessarily make that much of a difference. Because yes, here's a few different ways of doing the scan: full connection, half connection, weird combination of flag connections. but they're well-known approaches. It's not some secret that only we who are using Nmap are aware of, and those who write firewalls or intrusion detection systems are not equally aware of. So presumably, anything we can do with a tool like this, one can build a corresponding countermeasure tool to provide as little information as possible on those scans. And the Nmap documentation mentions that this doesn't actually work in Windows, which always sends reset, doesn't follow the spec, maybe for security reasons, maybe it's just the programmers at Microsoft, that always sends a reset in response to all of those types of probes, provides you no information whether something is open or closed that way. There's a couple others. There's an ACK scan that sends only the initial ACK. There's also a version of the ACK scan that also sends another field of the returned reset packet that can tell you certain things. Really just low-level analyzing of packets and determining a little bit more about what the host machine could potentially be. And that, to me, that's still interesting, as I mentioned, that, again, you have this spec, you have this RFC of what a TCP connections are supposed to look like, and they are implemented by humans with different perspectives, different goals, and just different ways of interpreting something written in English. And what you wind up getting is when you send a TCP packet of a certain type and you get a response, it's just a networking packet. But from that, and there's not, 50,000 different operating systems out there, right? There's a few dozen at most, and just a few of the most popular varieties, right? From those packets, you can actually gain information like, yes, this is actually a Linux machine I attempted to connect to, or this is a Windows machine I attempted to connect to. Even though in theory that shouldn't be the case, right? I send a packet, I get a packet back. Why should that tell me anything about the operating system I'm connecting to? That's one of those things that I guess if there was one implementation of a network stack that all computers in the world use, that would be a risky thing. But if that were the case, you wouldn't be able to do that necessarily because it's different implementations, intentionally sort of kept separate over sort of generations of development now. You do get different types of responses depending on the operating system. You can actually do more further enumeration of the devices just via attempting these connections. Seems kind of magical. It's just that there's some variety in these implementations, which if you're trying to look for those differences, you can make those determinations or really good inferences as to what extent a certain operating system is on a device. One more port scanning technique that I think is kind of interesting before we talk about other functionality. And again, we have the slides here. This is also covered in both of the book references you have access to on Canvas. It is also just a straightforward reading of the Nmap documentation. You could say, well, SciB 2310 was great today. He just read through the documentation for Nmap. Well, it's a really cool tool with a lot of features. So yeah, today we read through the documentation for it. But I added figures at the very least. This last one is called the idle scan, or the other term is the zombie scan for it, idle-si. It's also something of a subtle implementation characteristic that Nmap takes advantage of. It's also, I think, probably significantly more stealthy in terms of attributing which machine is actually attempting to perform the actual port scan. I think I have to walk through it a little bit slowly here. You could either just read the description or kind of zoom in and look at the actual diagram here. There's two things you have to understand how the zombie scan works. First off, as part of the IP, there is an IP identifier counter that normally we use just to keep track of statefulness of connections, but it's something we can otherwise rely on to reliably kind of increment for every packet that we're sending back and forth. So just take that for granted if you didn't know that. There's a counter that for every packet back and forth keeps incrementing. Take that for granted. The way this works is it takes advantage of a third machine, and it has to be a so-called idle or zombie machine, hence the name here. Another way to think about it, there needs to be an additional machine that's listed as the idle host here that's not otherwise attempting to do any sort of networking traffic. This approach doesn't work if it's sending even a single packet back out. What we can do with we call it attacker, our Nmap machine here, is we can send any sort of request to that idle host, and as part of the response, keep track of what that ID is, what that counter value was, 1, 2, 3, 4, 5 here. Connecting to a third machine that's otherwise not doing any work. has to be a machine you have some control or knowledge of. Presumably not the machine sitting right next to you, kind of defeats the purpose. Some other third-party machine that is otherwise idle. I'm just sending it a packet to get that unique counter back. I then forge a packet from my nmap machine saying, I'm actually that idle machine. Now to the host I actually want to scan and send my syn/synac to attempt my handshake at that point. That is forging a packet, right? There's nothing magical about TCP/IP that says that the IP address I put in the packet has to actually be my IP address. If you want to get any traffic back, it's a good idea, but it's not actually a requirement, right? It's just ones and zeros in a data structure in a programming language that gets stored in memory before it gets sent out over a wire. There's nothing preventing me, certainly if you have sufficient access on this machine, from crafting a packet that is actually saying the source IP is not actually my source IP. It's actually this machine's source IP. It's a little small here. Send something to the zombie, get that unique counter value back. Send something to we call it the victim, the machine I want to do the port scan of. You can think of it as a victim, that's fine. Claiming I'm that idle host. Well, what will happen from the scannee, the victim machine's perspective? It's getting an IP address. This isn't a wire, right? This is a logical connection over who knows how many hops to get from here to here, right? It's receiving a packet that says it's from an IP address. It's going to then either complete the handshake, not complete the handshake, send whatever it needs to send back. It's not going to send it back this way. It doesn't know anything about this actual machine. I forge the IP address if you want to think of it that way. I'm going to send my SYN request. My SYN-ACK is actually going to go back to that idle host. And in doing so, presumably the idle host is going to attempt to either reset the connection or complete the connection. It's going to do something on the particular connection there. And in doing so, it's going to increment that unique counter. This was packet 12345. Because it got a weird connection it wasn't expecting, right? And it's probably always going to send that reset, right? From the idle host, from the zombie's perspective, why are you sending me this? Who are you? Why are you sending me that SYN-ACK message? I don't even know who you are. Why are you sending me this? Here's a reset with 1, 2, 3, 4, 6. Then the third part of the way this actually works, and the reason it's somewhat more stealthy than sort of one of the default or other scans, is I just do that same IP ID probe again. And I get a third number back, 1, 2, 3, 4, 7. The way this works is by what didn't happen. We understand that there was something listening at that particular port. We got 1, 2, 3, 4, 5, and then next we got 1, 2, 3, 4, 7. We have learned, well, what have we learned? That there was a 1, 2, 3, 4, 6 packet somewhere is what we've learned, because the number supposed to increment, didn't increment, it jumped by 2. And again, that's why it's called idle. If this thing was otherwise doing all sorts of other networking traffic, then it wouldn't work. You'd get some seemingly arbitrary number back out, some higher number back out. If this is truly idle, this is 1 packet, 2 packet, this is our 3rd packet. We know without ever even directly connecting to that machine that it is listening. It's at least returning something to that request that was sent. And that's what's being shown on the right-hand side of this same exact slide here. We do the same exact sequence of operations here. If we were to do this and the port was actually going to be closed, it would directly not attempt a SYN-ACK. It's not attempting to connect at all anymore. It just sends a straight reset. That zombie, that idle machine, doesn't have to send anything in response. Consequently, when we do that additional probe here, we wouldn't get 1, 2, 3, 4, 7. We would get 1, 2, 3, 4, 6. We didn't skip one. In doing so, there is no seeming connection, at least one that's perceived from this machine's perspective. It may be able to perceive that there is some sort of port scanning attempt happening here, but not perceiving that you are the one doing that particular port scanning. It thinks this other zombie idle machine is doing that port scanning. So if that machine is the one sitting next to you, then what's the point? If it's some other completely arbitrary machine that you have control over, then you can have a relatively stealthy port scan of that host machine. Questions about zombie and idle?
There's some
This one here. This one. Just has to be something that's listening. So could be a smartwatch. I mean, it could be anything that has anything that has that we're interested in, basically. So yeah, we tend to draw them as being, here's the server we're connecting to, but anything that's got a connection is this would be valid for. It's intended to be a significantly stealthier from the perspective of this machine, which is labeled here as the attacker, the nmapper, us. I'm the one running nmap. This machine, assuming that this process and the one over here as well proceeds as expected, may be aware that someone is attempting to do a connection in port scan. It's receiving a packet here. Again, that arrow is not a physical arrow, it's a logical arrow. It's receiving a packet, but it thinks it's this other machine. IDS could say, well, I'm going to block this machine. I don't ever want to see a connection from this machine ever again. It's port scanning me. It's a very logical thing for it to do. It could block this host. Well, then if I want to do it again, I just find another idle host, and it's never aware that I am the one who is actually initiating all that. So that's what we mean by stealthy here. Again, not to get too metaphysical about it, but you can't deny that there's packets being sent. You can't do port scanning without sending packets. It's always loggable. It's always measurable. Something kind of physical ultimately sort of has to happen with the ones and zeros over a wire or wirelessly here. We can maybe limit how much information is gained by someone trying to detect that hack. Yeah. There's also the concept of UDP port scanning that Nmap allows, which we've talked about how UDP is useful for all sorts of things, including DNS here. As it sounds, you pass dash S capital U, you're sending a UDP packet instead of a TCP packet. It's kind of listed here, but this would be potentially significantly slower than any sort of TCP-based approach. Why do we think that's the case? While we look at a somewhat funny meme about this one, at least I like. Why would this be potentially significantly slower? Could be a large amount of data. What is that fundamental difference? UDP not only drops packets, UDP doesn't require there to be any handshaking or any other kind of mechanism that gives you the answer. It's fire and forget is what it says on the slide, which just means depending on the service, depending on the connection, it can be a very one-way thing. Meaning I'm a media server, I'm streaming a video over SMB or other things, SMTP, excuse me. I'm streaming a video. I don't have to get any data back. I'm just streaming the video as fast as I can. It's up to your client to determine how to process that data as it gets. So for that reason, there's arguably kind of a fundamental impossibility of doing UDP port scanning, because just because something is listening via UDP doesn't mean it ever needs to respond. So the challenge that Nmap as a piece of software has, it has to have some best case heuristics of trying to determine whether something is listening on UDP port and just ignoring you, or is it not listening on that UDP port? There is no reset, there is no fin, there is no flag like that to get on the way back. And I think that's, theoretically an impossible task to determine whether someone's ignoring you or not, not picking up the phone. I think the reason it's even somewhat tenable from a practical perspective is, yes, in theory, there's no way to tell the difference. In practice, when we talk about UDP connections, there's only so many things we do via UDP connection, and it can check for sort of common cases versus trying to solve sort of an insoluble problem of ignoring me or just not connected at all. But still, in order to do so, it does require a significant more amount of time of waiting, of saying, I'm sending these packets, I'm waiting. Does that mean there's no connection, or is it just ignoring the response or not having a response as part of that connection? And we're talking the difference, between microseconds, milliseconds, and seconds for every port that we want to scan here. So when I say slow, that's what I'm talking about. If I have to send and then wait 5 seconds to determine whether or not there's a connection or not, That's not too bad. Okay, I run the command, I wait 5 seconds. You got to kind of enumerate that out. What does that mean in practice when there's maybe 64,000 ports I want to scan? When there's maybe, well, we joked at 16 million, IP addresses we want to scan, but there could be on the order of hundreds or thousands of IP addresses I want to scan. Now, when you have that, you can just kind of multiply those numbers together. That's the joke of, that's a time-lapse video of 2 weeks of someone doing the scan. It's feasible if one isn't a little bit more precise and surgical with how they're doing the scan, that if you just blindly say, check every port of every IP address with every possible scan type, you just multiply all those possibilities and those permutations together, then the base case of how long it takes for one port on one IP address actually matters quite a bit, and those orders of magnitude matter quite a bit. We already talked a little bit about countermeasures. That's the whole point, at least to start, of intrusion detection systems. Everything that Nmap can do, presumably there's a piece of software that's like reverse Nmap, that's checking for the same exact thing happening on your incoming traffic. All those patterns can be checked and can be looked for. Sometimes the trade-off, which is difficult to manage when building such systems, when using such systems or administering them, is kind of the signal-to-noise ratio. If you have a firewall, and if you set up to generate the logs of the interesting, potentially port scanning kind of traffic on a machine that you own of a public-facing IP, you will quickly find, and I don't know if anyone here has done this before, the whole world is port scanning you all the time. And so there's this kind of signal-to-noise ratio of there's a whole lot of traffic trying to connect to you all the time. Where are the important concerns? When does it become an issue versus just something to log and move on from? So signal to noise becomes an issue here. Other mitigation approaches, of course, would be doing it yourself, right? We talk about from the pen tester's perspective, if I'm worried about other people port scanning me and determining what services I'm running, I should be checking it myself. Internal to the network, what's discoverable? External from the internet, what is accessible? And having policies that say, well, you're running this service on this development machine, should only be internal, should not at all be accessible externally, and be just continually monitoring those things. There's also fun kind of hacky kind of workarounds such as port knocking. The concept behind port knocking, the idea is like you have like a secret club or something, and to be able to get in, there's either a password, fine, we understand that analogy, or there's a specific door knock to get in. You have to go, and then someone responds, and then you can actually do the connection. No one followed me up on that. Thank you. Okay, I was just checking. That's door knocking with a knock code on the door. Kind of the same concept with port knocking. My understanding of it is it's more of like a clever thing to do versus something that's in common use. But the idea behind it is that only via a sequence of different port requests does one actually be granted access to connect to the intended service on the intended port. That's what it's kind of showing here, that here's one computer that's attempting to connect over port 23 to a particular host, and we get a closed response. We get a no back out. Whereas if that same host in direct sequence attempts 867, 5309, then port 12345, or just whatever arbitrary knocking, secret handshake, secret knocking sequence here happens, only then would it get a yes response on that port 23. It's sort of a security via obscurity kind of approach here, but one can imagine how that could be a countermeasure to that kind of just scan and see what things are connecting and not connecting. At the end of the day, you need to be able to provide a service that people are attempting to use and have access to. And if such a thing really became ubiquitous, it would become kind of a known sort of quasi-standard thing, in which case Nmap and other tools would also be able to connect and detect those things. But it's a clever workaround for that port scanning approach. I mentioned this briefly, but just to talk about it a little bit more, you can generally make some detections about what the operating system is. We talked about some TCP specific settings, but also just based on which ports are open, you can make some determinations here. This is just an example. If ports 139 and 445 are open, it's probably running some sort of Windows. This is also more of just like a good kind of Bayesian guess versus an actual truth of that. But because there's all sorts of well-known net BIOS things to run your printers and things like that using those ports, and it's sort of default, at least historical file sharing is running on port 445. Yeah, that's a good guess that it's probably running Windows. As part of Lab 2, you were supposed to see some aspect of that where Nmap, just via the ports it got back, gives you its best guess as what it's connecting to. And then we'll talk a little bit more about those lower level things that gives you a more precise guess. They are both just guesses, but you can get pretty far with intelligent guesses. Versus if we have port 22 and an NFS port open for our network file system, it's probably Linux. The word probably is doing a lot of work here. Statistically likely, in terms of all the machines in the world, what's the likelihood it's one or the other? There's nothing stopping you from running a Linux machine with ports 139 and 445 open, or running a Windows machine with port 22 and port 111 open. So it's not a proof positive that's the case. We're talking our kind of best inference in terms of, well, we get this open, that's probably what's running, and probably does get you pretty far here. Then there's actual low-level operating system detection. And for now, I think it's sufficient to know, like I mentioned, that there's a spec, there's an RFC, and it's developed. The software for it is developed over a period of time by different people with different interpretations or just different coding practices, or what we sometimes refer to as sort of different side channels inherent in the implementation, that just the actual literal low-level timing of the implementation can tell you some things about what's running here. So in Nmap, when we pass -O and then you have to pass some other options, it will do its best to use its low-level knowledge about the underlying vendor's IP stack implementation, TCP IP stack implementation, to give you a better, highly probable guess as to what operating system is running there. Again, there's not thousands of different implementations. It's on the order of dozens. And sure, if you were to create your own bespoke TCP IP stack for your own device, and that's what's running on your system, then Nmap's not going to be able to catch it. You may have all sorts of other vulnerabilities and other problems as you're doing it yourself, but it's not something that's going to be guaranteed to be able to determine what's not already in its knowledge base of here's things to look for various versions of Windows. And it's just a very empirical task of, based on what we tend to see when connecting to Windows 11, here's what we're seeing in these IP returns, IP packets. This is probably a Windows 11 device. Put this screenshot here. Nmap can detect it. Anyone know what operating system this is? It's Windows 3.1, which I've used. You know what? It had a lot going for it, if I'm being honest with you. It didn't really have networking support out of the box, so if you actually want to connect to anything. But the version, this is probably Windows for Workgroup 3.1.1. It had some networking added to it. There's some things that are probably better in that than modern systems. Very, very quick, very snappy. It did like 7 things, but it did 7 things really well. So, why do you need anything else? It's got a clock, it's got Minesweeper, it's got a file manager. What else do you really need, to be able to do what you need to do on a computer? But yes, Nmap can detect at least the networked version of Windows for workgroups, the early NT versions as well. So when we talk about enumeration, just means listing out counting things, right? We're enumerating things, trying to find more information about the underlying system or systems beyond just potentially what operating system it's running and what ports it may have open or not open. We saw that with the banner grabbing approach, where just part of the HTTP spec, it tells you what version of things that it is running. It tells you, here's the server, Nginx 1.23 or whatever it was. It's telling you in plain text what it is. But similar to what this allows you to do, which is based on certain characteristics of the returning packets, giving you some hints as to what kind of operating system is running, there's something very similar for attempting to connect over various ports with well-known services, that different implementations of an SSH server, for example, will have different characteristics of results, and you can use that to more further fingerprint what is actually running on the particular device. It also depends on it's really per service, it's application specific, but some applications will just kind of, by their sort of open and trusting nature, leak some information about the underlying system Again, just based on how they were originally designed. We're dealing with, again, decades of kind of, of implementation and cruft, and from a time where people really weren't thinking about the security considerations of these services. Probably if everything was a clean slate design today, you wouldn't have nearly as many of these kind of enumeratable services, but that's not the case. We still support all sorts of things that were defined many, many, many years ago. So port scanning tells us some things. It usually assumes kind of the known defaults for the so-called well-known port numbers. And I mentioned that to you. You'll probably be a little faster in the lab this semester if you have those committed to memory, at least the most popular dozen ports and what services they correspond to. And Nmap has those as well. And attempting with the -SV flag or -A for try everything will start to give you some additional information, potentially about, we talk about operating system, sometimes the actual type of device it's running on, also sometimes what kind of version number of the server that is actually running on that. And as we've talked about and shown in a couple examples, if you know the version number that of the service you're connecting to, now your next step is to figure out, this will be more of a Thursday topic, is there something vulnerable there? So I know I have a web server. Great. That's useful. That's certainly something we learned we didn't know before we connected via these mechanisms. I know I'm now using Nginx web server of version 1.23 running on Windows 3.1 or something. Okay, now I really know something about the machine. Now I can be a lot more precise in terms of looking where I want to go for what kind of exploits are already being provided here. I do want to talk about the Nmap scripting engine, but we can do that on Thursday. Then this is a clear connection to what we're doing next. We don't do a lot of that in the lab. Instead, we rely on Metasploit because it kind of provides a lot of really nice features for you beyond the scripting of checking for vulnerabilities. But let's leave things here right now. Good luck for those of you who are going to the career fair. We'll finish this up on Thursday, and it does much more directly connect to the next topic as well. So we'll do that right on Thursday. Thanks.